working? Okay, good. Okay, hello everybody. So first of all, thank you organizers for organizing this nice workshop and inviting me here. It's always a pleasure to be in Natal. And I'm at Stony Brook University and Simon Center for Geometry and Physics, supported by agencies. But the most important, of course, is the support of the team. Tankut Khan, Gustavo Monteiro, and Shriram Ganeshan, and Gustavo is a part of this workshop. And what I'm going to present is a part of some pretty long project already, which I'm doing with these guys. So let me start with some motivation. I'm going to talk about hydrodynamics, which is generalized, but not in a different type of way. I prefer to call it deformed hydrodynamics, so I'm basically kind of adding some additional term to make it still ideal hydrodynamics, but with some unusual odd properties, and I will explain it in detail. And motivation is coming from various examples that we know. For example, fractional quantum Hall effect can be considered as an exotic isotropic parity breaking fluid. And there are some other isotropic fluids with broken parity in 2 dimensions. And 2 dimensions is very special. I'll explain why in this respect. And generally, more general motivation is that variational and Hamiltonian formulation of fluid dynamics is a very powerful tool. And it's interesting how one should modify those formulations to include effects of broken parity. And there's a more specific motivation is there is a very interesting quantity which is called odd or Hall viscosity, which is known to be present in fractional quantum Hall states. And the question is how this Hall viscosity manifests itself in the bulk and boundary properties of these fluids. And most generally is the role of topological terms in boundary conditions. Let me describe this in slightly more detail. So we have recent progress in classifying topological phases of matter by mapping them in a topological quantum field theory. And this is about gapped phases, when the ground state is separated by well-developed gap from the excitations. So we have gapped bulk and then non-trivial protected boundary dynamics as a consequence of this topological order. And using mathematics of topological quantum field theory, we have quite detailed classifications of possible non-trivial phases. So what if we take some not topological state, for example, hydrodynamics in my example, and couple it through topological coupling to additional topological quantum field theory? Then, because there is nothing metric dependent in both coupling and the TQFT itself, then we do not change stress tensors this way. But some properties will change, and we all know that Poisson structural commutators of basic quantities change in the bulk, but also boundary conditions. So maybe we can now move ahead and consider not necessarily gapped systems, but having some particular state without gap, we can create the whole family of states coming out from coupling of this state with topological quantum field theory and use the previous mathematical classification to classify, for example, possible non-trivial boundary conditions for such systems. So this is like big motivations. You will not see much of it in my talk, although there are some connections. So there are some isotropic fluids with broken parities. This is just a few examples. Probably all the examples include plasma in magnetic field and helium-3A films, for example, if you want 2-dimensional systems. Quantum Hall fluids is another example. Vortex fluids, the fluids of vortices. If we have hydrodynamics with some non-vanishing concentration of vortices, then we can think of these vortices as forming fluid on their own, and we can study that fluid. And also another interesting application is chiral active fluids. If you think about some particular constituent particles which actively supplied by torque, so they're being rotated, then it turns out that they have very non-trivial hydrodynamics, which remembers about broken parity and has some interesting new terms in hydrodynamic description. So I'm going to talk about 2-dimensional fluids in this talk. Some of general things will be applicable to high dimensions, but mostly I will be focused on 2-dimensional fluids. So the contents of this talk. So first I will have some long introduction, so it will be like half a talk at least, where I will talk about fluid dynamics, variational principle, free surface, etc. So I apologize to experts, but people have come from different backgrounds, so I hope will be some useful parts in this introduction for many of you. And then I will talk about fluid dynamics with odd viscosity and odd surface waves. And I will explain what this odd viscosity is at that point. And then I will present our main result, which is variational principle with odd viscosity and free surface. So first, so that if you get detached from my talk, this is main result. So the main result, and it's not supposed to be clear to all of you except for people who know how to do variational formulations of fluid dynamics, but this is the action which I claim produces bulk equations for hydrodynamics, for compressible hydrodynamics with Hall viscosity, and also proper boundary conditions at the free surface of this. So this both bulk and boundary are described here. So I will explain more details here during the talk. Okay, so motivation number one, so introduction number one, hydrodynamics. So to get hydrodynamics, we need separation of scales, and basically we have emergent collective behavior, which is made out of microscopic motion of many particles. And so I'm kind of go ahead. And one important assumption that we need is that because of that separation of scales, there is a thing which is local equilibration. So typical quantity which we take equilibrates, relaxes very quickly to a local equilibrium characterized by a few local parameters, except for some conserved quantities. And because of symmetries, we can have locally conserved quantities, and those quantities relax slowly. So at the end, what we do is we will try to write equations only for those locally conserved quantities. And because we assume that there is a local equilibrium, we can relate those conserved quantities with each other. So we can express currents corresponding to those conserved quantities in terms of conserved quantities themselves. And that makes our system of equation closed, and this is hydrodynamic equations, and this is why hydrodynamics is so powerful. So when we do these constitutive relations, when we derive those constitutive relations or write them phenomenologically, the relations which relate fluxes with conserved quantities, we use also the idea of gradient expansion. So we assume that additional gradients in our equations come with microscopic parameter L, and we assume that this combination is small. So we often stop at some number of gradients. The typical hydrodynamics, which is every textbook starts from, is the hydrodynamics where there are no gradients at all. It's ideal fluid. And then we add this first order term, we get viscosities, and so on and so forth, as long as we can proceed. But the number of terms gets growing very fast, so we usually stop at first term. And finally, hydrodynamics itself is just local conservation laws plus constitutive relations, which are written with the use of gradient expansion, and that gives you a closed system. So let me stress the role of symmetries. The role of symmetries is twofold here. On the one hand, some continuous symmetries or broken continuous symmetries result in some slowly relaxing quantities and conservation laws, and these are hydrodynamic equations, the local conservations of those quantities. But also, another symmetries and these symmetries as well also result in restrictions on constitutive relations. If system is isotropic, then constitutive relations should respect this isotropy. So basically, this is the idea, and what I'm going to do in this talk, I'm going to use to study the role of parity in this respect. So in the ways how parity can restrict constitutive relations. So let me give you an example which probably was already been there, so in the very beginning of this workshop actually. So let me from this point of view explain how it works. So for example, we have one conserved quantity with density, for example, best density. We write local conservation of this quantity. So integral of rho is conserved because it's given to the integral full derivative of some quantity which is called mass current. And then we know that this is the only conserved quantity, so this current should be expressed in terms of density itself. You cannot express vector in terms of scalar without using gradients. So the first simplest term you can write was one gradient saying that current is proportional to gradient of density. And of course, this gives you diffusion equation. So if you have one conserved quantity, that generically it satisfies diffusion equation. And this coefficient, we introduced it phenomenologically here, but if you derive it from microscopics, for example, from gas, you will see that it's indeed the microscopic length multiplied by derivative. Okay, so this is example. This is an example which has more to do with what I'm going to say. This is example of barotropic fluid. So suppose that I have two conserved quantities, density and momentum density, which is vector. I write two conserved local conservation equations, two continuity equations, one for density, another for momentum density. Here, pi ij is momentum flux tensor, and pi ij and ji should be expressed in terms of density and momentum densities themselves. What we usually do is we relate them introducing velocity. We say that the mass current is density times velocity, and momentum current can be different, but if system is Gaussian invariant and it consists of one component, we just say that it is the same. That's typically what they do in the beginning of textbooks on Hydra. And then from Gaussian invariance and other symmetries, we say that momentum flux looks like this, where P is arbitrary function of density. And this is why fluid is called barotropic. Barotropic fluid in which pressure is function of density only. You can expand it and include thermal effect, temperature, etc. And what this hydrodynamics is a zero-order barotropic fluid dynamics. And if you just now substitute these constitutive relations here, you will get standard continuity equation. And from here, using continuity equation, you can derive Euler equation of ideal hydrodynamics. So this is a trivial example. What we are going to do is we are going to change slightly these constitutive relations by adding terms which break parity. So that's the idea. So now let me go to the second part of introduction. So variational Hamiltonian formulation. So in the absence of dissipation, fluid dynamics often has Hamiltonian structure, by which I mean Hamiltonian and Poisson brackets, which tells you how to derive equations of motion, and also allows for variational formulation in terms of some action minimization, of which gives you equations. It's more complicated in dissipative cases. You have to either go to Keldysh formalism or to do some not fully free variational principles, but I will not go into talk about. And Hamiltonian formulations is convenient and important for many things. It's important for quantization, but not only, it's also can be used for many particular problems in fluid dynamics or dynamical system theory. Variational principle also has advantages. It gives you the most covariant description. It's very easy to generalize it by putting it in curved spaces, introducing metrics and various type of backgrounds. It allows you for variational ansatzes. So if you know how fluid moves approximately, you can substitute this and then minimize over the rest of the fields, and you will get equations describing how this ansatz and so on and so forth. And also useful in numerics, because when you have just some quantity which you have to minimize, that's very convenient, especially if it includes also boundary conditions. Important topic here is the various type of reactions. So first of all, relationship between Hamiltonian and action is not very straightforward in fluid dynamics. That's why it's usually considered to be subtle. For example, if you know the Hamiltonian and Poisson brackets, you cannot directly write action for fluid dynamics, which we usually just write PQ dot minus H, but it turns out that it's not so easy in this case, and I will explain why. The reason why is that Poisson brackets for fluid dynamics are degenerate. They have the things which are called Casimirs, which Poisson commute with all quantities. And therefore, when you write Hamiltonian, you have to invert Poisson structure, but it has zero modes, so inversion is not so straightforward. And technically, it's called Hamiltonian reduction from infinite symmetry groups. I will mention which groups, but I will not go into detail. Also, Gustavo Monteiro gave a talk last week within this program and explained some of these technical details in his talk. And we also deal with some type of reductions. For example, we can start with compressible fluid, then assume that it's incompressible, or superfluid, or whole fluid, and look at the boundary dynamics. So you can start with some more general hydrodynamics and then reduce it to various particular cases, which very often very non-trivial. So I will now illustrate the Hamiltonian variational principle as the example of barotropic fluid, which we already considered, very quickly, and then I will go to whole viscosity. Any questions? So by the way, interrupt me at any point. Yes? Barotropic means that pressure is a function of density only. It's not, usually pressure is a function of density and entropy density, for example, or function of density and temperature. So if we just say that pressure is just function of density, that's barotropic. Okay, this is Hamiltonian structure of barotropic fluid. I claim that if you consider these Poisson brackets between density, 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 velocity, and velocity, velocity, notations here is that if I write rho, it means rho of x, and if I write rho prime, it means rho at different point x prime. So this is the system of Poisson brackets satisfying Jacobi identity. Everything is fine with that. Then, having Hamiltonian, we can generate equations of motion by taking the Poisson bracket of Hamiltonian with any quantity q. And the claim is that if you just take this Hamiltonian and Poisson commuted with density, you will get continuity equation. Poisson commuted with velocity, you get this equation, which is Euler equation. And pressure here is expressed in terms of the energy density epsilon in standard thermodynamic way. Okay, so this is the answer of how to write Hamiltonian for infinite fluid. Yes. Okay, so the interesting way, I still am looking for all the references, but the earliest reference I know is 1947, Landau, who was considering quantum fluids, so he derives these commutators from quantum commutators, and then you can take h bar going to zero limit. That's one of the ways. But you can, of course, do it classically. So essentially, one way of which I know how to derive this is from microscopics. Very simple one. You just write that microscopic density is sum of delta function at positions of particles, momentum as well, and then you just Poisson commute. That's one of the ways. So it depends on what starting point. So it's I know. So for example, you can ask if you have action, can you derive to Hamiltonian from action? That's another possible route. But then you have to find out how to come up with action. And so there are many ways depending on starting point, but the easiest one is to start from microscopic description and do this algebra. If you have some set of equations, then I don't know how to do that. Yeah. Yeah. Right. No, there are a lot of subtleties here. Usually subtleties appear not at this level, but at the level when you want to write gradient correction to it. Then there are a lot of subtleties. At this level, this is very straightforward to do from microscopics. Of course, I always assume that those microscopic densities, basically I write some microscopic expressions, I do algebra, and I see that I just get this exactly, and I see that nothing here knows about the number of particles. So I'm saying that if I properly smoothen all fields, it's the same. And this is a little bit subtle point, but yeah, I agree. So, but now when it's written and this is written, you can just check that it produces hydrodynamic equations for motion. Yes? It's basically whenever you can neglect thermal transport, heat conductance, it's like air. Yeah, it's just simple cases when you do not compress it too much so that it doesn't heat. So it's really not so bad. But also it's just illustration. I can add here rho comma s, where s is an entropy density, modify it just a little bit, and I will produce the full system. So it's not a problem. It's just illustration. So we can include temperature effects here easily, but no dissipation still. So it's like it will be fluid or gas which can move, it can heat, but it's all adiabatic. So there is no heat conductance. There are no dissipative effects. If there are dissipative effects, then by writing Hamiltonian, you have to write relay dissipative function and so on and so forth. There's separate. I'm talking about ideal fluid today, so my task is simple. Okay, Casimirs. It's actually in 2 dimensions. By the way, the previous stuff is in any dimensions. It's not necessarily 2 dimensions, but in 2 dimensions, it's known that there are infinitely many quantities which are called Casimirs, which are written here. It's integral of a density multiplied by arbitrary power, arbitrary function actually of vorticity divided by density. Vorticity is a curl of velocity. So if you just take this quantity and find Poisson bracket of this quantity with density and with velocity, then you'll get identical 0. It means that this quantity is conserved for any Hamiltonian. So it's not conserved because because it's the symmetry of Hamiltonian, but it's the property of Poisson brackets system. So it means that there are zero modes in those Poisson brackets. And this is the obstacle of getting from Lagrangian to Lagrangian. Let me remind you how we usually go. If we have just simply Poisson bracket of P and Q to be some number kappa, then Hamiltonian is, and I know Hamiltonians, then Lagrangian is just 1 over kappa PQ dot minus H of PQ. And that's Lagrangian, where you substitute instead of PQ dot and so on and so forth. But you see that if kappa is 0 for some pair of variables, then 1 over kappa doesn't make sense and there is a problem. And the existence of this Casimir shows that there is a problem. So it's not that easy to go to action from here. That's right. It's like Casimir for rotational group L squared commutes with everything. So it's a group of diffeomorphisms of the fluid. Any questions? If I relax barotropic conditions, it will be replaced by some other Casimirs. But okay, so let me explain where these Casimirs are coming from. What's the reason for their existence from symmetry point of view? And there are two descriptions in hydrodynamics, very useful ones. One of them is Lagrangian, when I'm just saying the following, that I have some mathematical plane phi with coordinates phi, and I have time-dependent mapping of this mathematical plane into physics plane x. So like if I have some point here, it will be mapped into some point here, which will evolve in time. So this I think of the physical space, and this is of my fluid, and these points are fluid particles. And my full description is just x as a function of phi t, the mapping, time-dependent mapping from this plane to this plane, and this is called Lagrangian description of fluid. So and then knowing this, I can determine positions of all fluid particles at all times. And the Eulerian description is different. If I just look at the physical plane and I look at the fluid particle and its velocity, then I can just ask what is the value of velocity, what is the velocity at this particular point as a function of time. And that's called Euler description. That's what I used before, the equations for velocity and density for this description. Pretty clear, well, there is, first of all, exact relation between those descriptions. Velocity of fluid at point x is just x dot taken at point phi, but phi is substituted as an inverse function of x. So it's clear that if I look here, the motion of this fluid particle right here, velocity here, does not depend on how I label. I can take a mapping of this phi plane into itself, relabel the ways. This doesn't affect what's going on here. Okay, yes? Vk of, no, Vk is the k component of velocity at this point, which is function of all coordinates. This is all coordinates of the point. Yeah, xi, I should put this, whatever curly brackets showing that these are all coordinates. But okay, so what we see is that huge symmetry, which is the any diffeomorphisms of the phi plane, essentially, or actually discrete symmetry, discrete relabeling is possible. But so we have relabeling symmetry, and those Casimirs are the conserved quantities which follow from this relabeling symmetry. I will not go into detail about that. I hope that Gustavo talked more about this stuff. So what I'm going to do is concentrate on Eulerian description, but remember that those degeneracies are from some additional symmetries coming from reduction from the Lagrange description to Euler description. Example of this type of structure, you know from classical mechanics classes. So if you have a top, that generally to describe the position of the top, you need 3 angles and 3 angular velocity components. So phase space is 6-dimensional, but you can consider axis attached to the top and write equations for the angular momentum components projected on the axis on the top itself, and you'll get 3 equations. So if I give you Hamiltonian for those, which produces those 3 equations, that's easy. But then I ask you to write what the action is. You have to remember that you have to write action in 6-dimensional space. So basically, this is the idea. So if I have something degenerate Poisson bracket structure, generally the idea is that I have to enlarge my phase space write variational principle on that in large phase space, and then because of some additional symmetries, my dynamics will be still confined to some particular subspace of that high dimensional phase space. Okay. The answer is this. So for barotropic fluid, the claim is that if you take this produces all equations. Let me explain what these notations are. That's the most important part. So this u mu, u0, or ui is just notation for this combination of three scalar fields, theta, alpha, and beta. So for example, u0 here is theta dot plus alpha beta dot. So theta, alpha, beta are known as Clebsch parameters. So notice that if you take variation with respect to velocity, you'll get v equals u. So essentially, this is the parameterization of velocity. And notice that I parameterize two-component velocity in terms of three scalar fields. So this is my enlargement of the phase space, which I was talking about. And also notice that if you shift alpha to some derivative of arbitrary function of beta, and I shift theta by theta minus f of beta, then u will not change. So this is relabeling symmetry, some part of relabeling symmetry. So whenever I do these transformations, u does not change. So my action depends on theta, alpha, beta, but only in this very specific combination. And that's the key. Okay? So now, technically, if you just take this and vary over velocity, over vi, you will get that vi is the same as ui in this case, and is given by parameterization in terms of three parameters. If you vary over theta, which is here and here, then you will get continuity equation right away. Now, it's a little bit more difficult, but if you write equations varying over alpha, beta, you write all these equations, and then take the derivative of velocity, which is given by this, and do a lot of, or not a lot if you are smart and know how to do it quickly, like Gustavo is doing, then you end up with. And remarkable part here is that, in principle, this equation could depend on theta, alpha, beta separately, but it depends only on the combination which is given by vi, and that's because of that relabeling symmetry. So that's. But technically, just everyone can check that this works. Any questions? So this is, I presented Hamiltonian formulations and action formulation for barotropic fluid dynamics. And again, so far, you can include temperature everywhere. I just did it to simplify formulas. This is so far in any dimensions, yes. Yeah. No. One dimension is much easier because in one dimensions you don't need excessive parameterization. In one dimension, any vector can be written as just gradient. So it's actually much easier. So you don't. There is no this excessive. Right. 2D becomes non-trivial. There are no Casimirs of this type. Yeah. It was, as far as I understand, it was originally guessed, but there is a more geometric way of deriving this. It's called Weber transformation. So what you do is you start with those hydrodynamic equations with this one in continuity, and you say that this is not really nice. You have to write it in terms of Lie derivatives. You write it doesn't work. You say let's introduce this parameter which helps, and then you end up with equations. And those parameters that they introduce are theta, alpha, beta, and so and then you end up with some system of equations for which it is easy to write variational principle. But there is another way also when you just say something like this, that you say, okay, obviously Hamiltonian is rho v squared over 2 plus epsilon of rho, but you also have to impose continuity equations. So let's introduce parameter theta such that theta times this added to Hamiltonian. So there are ways to do it. It's not always systematic ways. So again, if you just give me system of equations, then generally it is a very hard problem to find the action from which the system of equation follows. For this particular case, it's known, tricks are known, but general questions, I don't think there is answer. Yeah. Yes, you can. Theta is the velocity potential, essentially. So it's no alpha beta, then vorticity is 0 automatically, right? The curl of gradient is 0. And this alpha beta can be thought, that beta can be thought as a coordinate in that Lagrangian space, and alpha is velocity conjugated to that coordinate. So again, to find the meaning of this separately, you have to go to this Lagrangian formulation. If you have superfluid, you can forget about this, and you just have this, yeah. But in superfluid, you think of this state as compact, so that vortices is allowed, and it's a bit, yes. Who was canonical? Density and theta were canonical conjugated. Yeah, let me go to. You see, there is a derivative here. So canonical conjugated, we call that rho in pi equals delta function. That's canonical. Let's commute to 1. So this is v is gradient of theta. So rho and theta are canonical conjugated. Right. This in one dimension that works precisely like this. With this one, it's only it's not that easy. Okay. So this just works for now. So boundary conditions. Let me go quickly here. So usually we use various type of boundary conditions. Generally, hydrodynamics. If you look at classical hydrodynamics, it's not only about equations. It's mostly about various type of boundary conditions, various type of geometries, and you solve those equations within these geometries. But for this, you need to know what boundary conditions are for those equations. And typically, we have something like impenetrable fixed wall of some kind, where boundary of the domain is fixed. We say that normal velocity, for example, vanishes at the boundary. There are various other versions, but typically, we just say that this is hard wall. Fluid doesn't go through this wall, so normal velocity vanishes at the boundary. It's called kinematic boundary conditions in this case. It can vanish at the boundary. This will be a wall with friction, or boundary which is smooth surface. So that's what typically people do. And there is also another part of condition which is called free surface boundary conditions, when the boundary itself is a variable. It can change in time. And normal velocity at the boundary is equal to the normal velocity of boundary itself. It's just kind of definition of boundary of some things. It's called kinematic boundary conditions for free surface. And in addition, we take a small piece of the boundary and say that both normal component of the stress and tangent component of the stress should vanish at the boundary. Otherwise, this auxiliary mathematical piece of the boundary will have infinite acceleration. So that's what we usually do. This is what I will call free surface boundary conditions. There are some additions. If you have additional surface physics, for example, surface tangent, something actually happening on the surface, then you modify those conditions a little bit. For example, to normal component of the stress, you add this surface tangent force. Okay. So this is how it looks like. So we have fluid in some domain. There is a surface which I parameterize by this function. This is the kinematic boundary condition telling me that the velocity of the boundary and velocity of the fluid at the boundary have the same normal component. So essentially, if I look at the particle here, the normal component of its velocity is basically the displacement of the boundary itself. If fluid particle lives on the boundary, it will stay on the boundary. So in terms of H, this is just this. And dynamical boundary conditions is that I have to take a stress tensor and take its normal normal component, and will give me the stress force at the piece of the surface. And both components of this force should be 0. Both normal component of the stress and tangent normal component of stress should be 2 conditions. Okay. And the remarkable thing is this action, which I already wrote, but just restricted to the finite domain. So in y, I integrate from minus infinity to h, not to infinity. That also presents the free surface boundary conditions for ideal fluid. Okay, and this is known as Luke's paper is of 1967, but I think I know a paper of 1930 something which has the same result. H is dynamical variable. So this action, I missed it here. This action depends on the following fields: at rho, theta, alpha, beta, vi, and a. So, and you have to vary with respect to all of them, write all equations, and you get it. So let's first vary in bulk, then you have those functions of motions that I already presented. Then if you vary over theta, but remember to keep boundary terms, you will produce kinematic boundary condition immediately. If you vary over h, you basically will get that this combination is 0 at the boundary. It's very easy. But this combination on equations of motion is pressure. One can check. So you'll get pressure equal to 0 at the boundary. And because in this particular case the stress is just pressure, then the tangent component is automatically satisfied at 0. So this is a remarkable feature of ideal fluid. As soon as you add viscosity or some terms like that of high derivatives, this is not true anymore, and this will be resulting in some difficulties. Okay? So action is both bulk. Some quick remark. And I have constitutive relations that momentum density is rho vi, and stress tensor is pressure times delta ij. So this is ideal fluid dynamics in this. It's remarkable again that I can just take the same equation and just say, let's suppose that somebody told me that momentum, but rho vi plus some coefficient, this is just number, multiplied by skew derivative of rho. The star notation means epsilon ij times aj. And this is specific for 2 dimensions already, that you can see. If I do this, then I will just say that substituted here, use these equations. And what I get is that I can put equations in the same form as before, but here it will be p tilde, and here will be t tilde, and t tilde is given by this. So there is some ambiguity depending on whether what identification of momentum density I have. I have either this stress tensor or this. Equations are absolutely the same. Okay? So you have to be a little bit careful. So you should really identify your momentum density from either microscopics or state it phenomenologically or couple it to some proper background which tells you what it is, but ambiguity here. Here, by the way, there are this new coefficient. This addition changes 3 terms: the green one, blue one, and red one. So the green one is the correction to pressure proportional to vorticity. I usually like to call it odd pressure term, odd because it breaks parity. And this term is whole viscosity term, which will be my main hero for the remaining part of the talk. And this one is asymmetric part of the stress tensor, which tells you that whenever you compress or dilate fluid, there is external torque which is necessary for that. Okay. So what I'm saying is that although bulk equations will be absolutely the same, but for boundary conditions, I have now to put this to be 0 at the boundary. So boundary conditions will change. So you really have to be careful what's the identification of physical quantities. That's just a remark. Okay, now we can see the 2-dimensional fluid, which is compressible, isotropic, periodic, and has non-vanishing odd viscosity, and other coefficients will be 0. Okay. External magnetic field or Coriolis force, no rotation of the fluid as a whole, so no gap in the bulk. So this is not directly applicable to quantum Hall fluids. Consider this an exploration of the effects of odd viscosity only. And I also do not include all odd terms, so I concentrate specifically on one term. People like Andy Lucas were trying to analyze what other possible terms you can add and look at different effects. This will be focused on the one term, but in more detail and including free surface. Yes? It's just, if you look at the sound propagating in the bulk, it's compressible fluid. It can be like in plasma, separated by the gap, starting from non-zero energy or linear. Also will be to write variational principle, Hamiltonian formulations, and boundary dynamics for this system. So just a little bit explanation of this odd viscosity physically is. So the typical viscosity is the following. If you have a shear flow, so velocity goes like gradient of velocity, then usual dissipative shear viscosity, it says that whenever you have this gradient of velocity, you have a force, sort of friction between layers, which opposes velocity and trying to equilibrate it and make this shear vanish. And because it's against velocity, it performs negative work, so it's dissipative. So if parity is broken, and only if parity is broken, you have additional option of having this extra force normal to velocity direction. So whenever you have shear, you have compression. And because it's compression, not expansion, not extension, then this means that I know right from left I have to have broken parity. Otherwise, I cannot choose where the compress or extend. In other words, to write operation, this is how this term is written mathematically, and this star is a convolution with epsilon ij, which again knows right from left. A remarkable feature of two-dimensional fluid, then in 2 dimensions it's possible to break parity without breaking isotropy. So if you think about 3 dimensions, for example, and you want to use epsilon ijk, then you will be able to contract one index, there will be one left. You have to contract it with something, and for that you need additional vector. And for example, plasma in magnetic field, it's good, but magnetic field is vector and it breaks isotropy. So in a plane perpendicular to magnetic field, you will have similar to dimensional dynamics, but the magnetic field itself breaks isotropy. You need 2 dimensions to have isotropic fluid. Okay, bless you. So compressible hydro with odd viscosity, efficient for odd viscosity. Identify momentum density as rho vi as well. It's very results might change. It's straightforward to generalize. So viscosity term, but I will neglect the shear viscosity, so I will just write this, and this is totally dissipation-less fluid dynamics. And the boundary conditions are, as usual, free surface boundary conditions explained before. And that the derivative of pressure with respect to density at the equilibrium density is the sound velocity squared. So I will use the CS parameter. And one particular limit I'm interested in incompressible limit when the sound velocity goes to infinity. So the first thing what happens as soon as you have any viscosity term, not necessarily this odd viscosity, with shear viscosity as well, is that if you look at the textbook of derivation of surface waves, what they do is they say, suppose that velocity is potential, so no vorticity, velocity is gradient of some potential, and then you just write Bernoulli equation, and then you derive the plus minus square root of gk dispersion for ocean surface waves, right? For gravity waves in deep fluid. So now, as soon as you add small viscosity, you will see that it's not possible anymore, because with potential fluid we just have one boundary value of the potential one function to satisfy 2 boundary conditions for normal stress and for tangent stress. Before viscosity, tangent stress was automatically 0, so it was not a problem. But as soon as you add viscous terms, you will need to satisfy 2 equations, so potential flow is not possible everywhere. So somewhere, hypothesis of potentiality should be broken, vorticity should be present somewhere. The minimal way to resolve it is just to say that those tangent stresses at the surface create vertical boundary layer, very thin layer with non-zero vorticity at the boundary of the surface. And this was done by Lem in 1932 with shear viscosity. And what we found is that Hall viscosity modifies the structure of boundary layer. The physics is the same, boundary layer is formed, and that helps you to solve the problem, but it's more singular than in the case of shear viscosity. So because waves moving like this create tangent stresses, then vorticity in our boundary layer diverges in the limit of incompressibility, while it is finite in Lem's case. So that's a big difference. What we are going to do is we are going to look how it modifies the boundary layer, and we are going to write equations for effective dynamics of the boundary, assuming that this boundary layer is very thin in the incompressible limit. So, and this, of course, were done in regular fluid with shear viscosity. What you get there usually is that dispersion is the same square root of gk plus 2 times shear viscosity times k squared with imaginary unit, which is slight damping of the surface waves. But in this case, there is no damping, so we expect corrections to the dispersion, which are real. there are a lot of hydrodynamics is very complicated subject. So so if you just take numbers and in the ocean you just estimate the thickness of this boundary layer from numbers, you'll get something like fraction of a millimeter. This is nonsense. It's much bigger, and the reason is interesting because of corrections by fluctuations, you really have to renormalize your viscosity, and at different scales this viscosity is a little bit different. So it's actually much bigger than you would see from molecular viscosity limit. And one. Is it better? Yeah, it works. Okay, so this is a picture, no vorticity in the bulk, vertical layer at the boundary, and the thickness of this layer scales as 1/CS. CS is the sound velocity in the bulk. So in the incompressible limit, it goes to 0. But vorticity within this layer typically scales proportional to CS, so it diverges in this limit. But the product does not depend on the sound speed. And what it means is that essentially in that limit we will get the jump of tangent velocity at the boundary. And what we found is we just solved linearized equations following Lem precisely, just replacing one viscosity with the other. It turns out that many formulas can be obtained by just replacing nu even by I times nu odd. So it's like imaginary, like sigma xy is imaginary part of conductivity. And we found that there is a mode of the surface where on the boundary and the limit of small k, even in the absence of gravity, even in the absence of confining potential. This is quite interesting because usually in the usual fluid, if you don't have gravity, you just perturb the boundary, it just stays like that. And there is also this mode here. If you just perturb the boundary and velocity, initial velocity is 0, it stays. But you can also create this vertical layer in such a way that there will be wave which propagates to the left. So this absolute value of k should remind you the Benjamin-Ona dispersion, for those who know, is that the group velocity derivative with respect to k is always negative, so it's always propagating to the left. So there is one left propagating mode, even in the absence of confining force. And this is our older project, which is published. It turns out that you can do nonlinear corrections to this. We really hope to find Benjamin-Ona solitonic solutions and so on and so forth. No, it didn't happen. We found this equation, which of course reminds you Burger's equation, which already was mentioned in several talks. The few differences. So first of all, U here is a complex field. So it's a complex Burger's equation. Secondly, instead of the shear viscosity here, it's I times odd viscosity. So it's imaginary coefficient here. And thirdly, this U by construction of this equation should be such that it should have no singularities in the lower half plane. So we used to call it complex Burger's equation with purely imaginary viscosity satisfying conditional analyticity conditions. But then Chiral said that let's call it Chiral Burger's equation. It's much easier, and it also it propagates always in one direction. And the relationship of this complex U with original degrees of freedom is that basically the real part of this U is the horizontal velocity of the fluid at the boundary, and the imaginary part is vertical velocity of the fluid at the boundary. And you can solve this equation similarly to Burger's. To solve Burger's with viscosity, you need Kohl-Hopf substitution, which brings Burger's equations to heat equation, to diffusion equation. If you do the same substitution here, you'll get Schrödinger equation, extra I in diffusion equation. It's interesting. but also Schrodinger equation with analyticity conditions that psi is analytic in the lower half plane. And you can find a lot of partial solutions. You have find something like soliton solutions, but they're not quite solitons. For example, if you start with initial configuration which corresponds to 2 poles in the upper unphysical half plane, so analytic function which has 2 poles in the upper plane, and look how it evolves, then one of these poles in finite time hits the boundary and singularity develops. So this is not full equation. You need to have higher order corrections to stop this from happening. So it's not fully solves the problem. Typically, dissipative Burger solves the problem in the sense that instead of total shock waves, you have shock waves with smeared front. This one helps a little bit, but not fully. So you really need to find extra terms. We didn't. Okay. Yes. Okay. So what to do with variational principle in the bulk? The answer is very simple. We just add one additional term here, which is Q derivative of density times velocity. Parts, you also can say that this is density multiplied by vorticity. So if you add this term, the bulk equation but this odd viscosity term. It's as simple as that. But if you now look at the boundary conditions from this action, you will see that they are wrong. The tangent velocity should be 0, but it's not 0. Its tangent stress should be 0. This is like no slip conditions that you get from this action. So we have to add, but this something can be only involving boundary because bulk is already worked on. And the answer is that this is what you have to add. It's very interesting. This rho tilde is just the density taken at the boundary. Instead of y, you substitute h of xt. That's the easy part. So the shape of the boundary explicitly here, ht. But it turns out that, and it was surprising to us, and this is what takes some time, that you need to introduce some auxiliary field phi, which looks like a chiral boson, actually. And this phi is absolutely necessary here to restore reparameterization invariance of the problem. For technical reason, it's necessary. Some ideas of what it physically means, but not of this is confirmed formula. So I'll maybe answer questions if it will be. So the answer is the following: that this is a full action, produces both tangent and normal boundary conditions, and also bulk equations. So adding temperature external gauge field to the external magnetic field is rather straightforward, so one can study this generalizations as well. One direct consequence of this is that from the action, it's very easy well, it's relatively easy, at least from the bulk action, to get Poisson bracket structure. And if you look at what was done, let me look at the action. So as a bulk action, you see all time derivatives are here, field. So basically, for the field U, the Poisson brackets are the old Poisson brackets, but it is different, and it modifies brackets for rho and v, and that's why equations of motion is different. What you can say is that if you take vorticity made out of the mirror in the bulk, we still do not know yet whether boundary will lift this degeneracy of Casimir's. We are working on this. So this is only for bulk part, the Poisson structure for bulk part. And if you change, if you add external magnetic field, then you change vorticity to vorticity plus magnetic field here. So the Casimir will be like this. And that should remind you, if you know about this whole constraint, this is a property of quantum Hall fluids. Okay, so that's what I just said. So similarly to topological terms, odd viscosity does change boundary dynamics in a very profound way, but does not change too much in the bulk. The energy is still the same, rho v squared over 2. So there are many projects which we did, many types of actions. In particular, a very interesting part which we did with Gustavo recently is we just considered incompressible fluid at total incompressible fluid right away, and we did not add any shear viscosities, and we just said let's phenomenologically construct some effective action, and we added purely geometric action which basically proportional to the velocity of the boundary. If you add it to the action, it turns out that it modifies normal boundary condition in the right way. But I'll talk about a lot. My conclusions are here. So Carl Burger's equation describes weakly nonlinear dispersive dynamics of surface waves in such fluids. Some exact solutions are known, many more can be found. Variational principle constructed, and non-trivial boundary term is added, which is most interesting, and as the odd viscosity terms modify conventional Poisson brackets in Hamiltonian formulation. Thank you.
Thank you very much. Very nice talk. Are there any questions?